Welcome to this tutorial series where I will show you how to use the AI toolkit for analyzing and visualizing results of machine learning analysis that were performed on data retrieved from the NOMAD archive. We will demonstrate such analysis on a notebook that you have already seen from previous tutorials. That is the Query NOMAD archive notebook, where we have seen how to retrieve data from a NOMAD archive. And now we built a Pandas data frame, and now we are going to use that data frame for performing machine learning analysis. And more specifically, I will show you how to use the visualizer that we maintain at the NOMAD laboratory. We'll start from loading the data frame as a case results. If then you're interested in knowing how this data frame was built and how to retrieve the NOMAD archive, you can find this information in other tutorials. And now we are going to analyze the content of the data frame using some of the Pandas tools. So here we have the describe function that shows count the total number of entries and some statistics about the different quantities in the data frame as the mean, the standard deviation, the minimum, different percent. And this for all the quantities, atomic density, the atomic radius, and the convergence energy difference. Now we would like to analyze some of these quantities with more detail. And again, Pandas allows us to build very easily a histogram where we see we can inspect the space group numbers, and we see most of the compounds only are grouped into two different space group numbers. So there are essentially the 221, 227 space group numbers present in our data set. Still, we also see how the atomic density is distributed, and then that's the distribution as a histogram. Now, as a next step, we are going to group this data. That means that we are averaging over different entries with the same chemical composition. So you might ask, why do we have different entries with the same chemical composition? The point is that several users might have investigated the same material, but the simulations might have been with different settings. But even the same user might have done several simulations with different settings, always for the same material, and uploaded all the materials. So to facilitate the machine learning analysis, we only consider that one entry has only represent only a specific material, and then we average for all the others values that are materials specific as the atomic density. Later, we are going to perform unsupervised learning analysis. If you're interested in unsupervised learning, we have an exploratory analysis notebook where we describe in detail all these techniques. Here we are doing some clustering and dimension reduction, and as a clustering method we use HDB scan, while for dimension reduction we use UMAP. Later we are going to analyze the results of this analysis using the visualizer that we maintain at the NOMAD laboratory. This visualizer requires, in addition to the data frames that we've created, also a list of different features. Those features are essentially columns in the data frames. And we have some other features that are listing what are the features that can be inspected over materials over hovering, and the color features that will allow us to color the entries according to the values of the specific quantity. But now let's see more detail, then it's going to be more clear how this visualizer works in practice. Okay, so this is the results that we are obtaining. As we can see already, we have some interesting results. So we see some quite nice clusters with different colors. So the clusters, like the positions of the points, have been found by the embedding method, in this case UMAP, colors are given by different clusters, HDB scan in this case, and we can see that also there is some correspondence between different clusters in the position, spatial position in the map that are given by the dimension reduction and the colors that are given by the clustering algorithm. In this case, we have three clusters. By default, outliers that are also detected by HDB scan are not shown. But if we wish to visualize also outliers in this map, we just click onto the outlier's name onto the right, and those are then visualized. So now we would like to perform our analysis. First of all, we can change the marker colors and see if there is some insightful results into this clustering. And we then select the space group number, and we can find that essentially different clusters have different colors. This means essentially that each color represents a different space group number. So here the green color, you can see that the space group number is 221. Again, here the space group number is 227. So now we might even, as we can see now that the different colors represent the different space group numbers, colors don't represent anymore the clustering, so we cannot select which clusters to visualize or as we could before. And we cannot decide if including the classes from the list to the right. We have this specific box that if we can click, we can include those layers in the visualization or remove them. Then we have the different colors here that we can choose. So each color, in this case, we don't have, as the space group number, we have few different values. So probably it's not that useful having like so many bright colors. So let's see something different. Let's see with atomic density. We can see a gradient. This is already more interesting. We can see that already the disposition of UMAP is somehow find some order structure that are somehow ordered according to increasing atomic density within each of the clusters. Then we can also use, there are many of these colors, and that's you can just pick the one that you prefer. Let's come back again to the clustering here. So now here to the right, we've seen that we could include or exclude outliers, but on the other hand, we just can include, we can just see only one specific cluster. This is something that we can do, or remove it, or include it again. This all by clicking on the list to the right. This visualizer is built upon Plotly, that is a very popular Python library, and so those functionalities are given by Plotly. So now we can see our classes, but we would like to inspect the materials. So by hovering, we can see a number of different features, but now we would like to visualize the structure, the atomic structure of the material. So if we click on this material, the structure has appeared here. Below we have these two windows that use JSON-Small for visualizing structures of the different materials. So in this case, we can also use all the functionalities of JSON-Mol. So to make an example, we can change the color of the background into white. And this allows for a better inspection. Then we might want to compare different structure. Then we can use the windows to the left. And this is by clicking this box all to the right. And again, clicking on any of the compounds here will show a specific structure. We have seen before that we might have different compounds for different with the same chemical formula. And this is what represents this replicas value here. Now we have 4 replicas. we click this compound that it was displayed to the right has different 4 simulations with the same chemical composition for the same material. And if we want to see the different structures, we just have to click on display. If we click on display, we can see how all the 4 different structures that were uploaded, that were found. So the count in the machine learning analysis, all the values were averaged, but since we don't want to lose any information and we might want to recover the different structure and see if there were major changes, we can analyze each of them by clicking on this display button here. Still, we can use this visualizer also for doing the opposite thing. So we might want to look for a specific material, and we can insert the value of the material that we are looking for in this window here. Then by clicking on display, this will appear somewhere on the map, in the exact position of the map. And then we can find it starting from the equation, from the formula of from the chemical composition. Again, we might want to compare it with another material, and this is again, and then we can find something that apparently they're also very close. So now we can go like this, getting closer and see these 2 materials on the map. So in this case, we find those are both outliers. They don't belong to any cluster. We might be interested in see also these other compounds if they have some specific structure, and then we might see why they are all placed in this position. So now we use this visualizer for our machine learning analysis, and but then we also might want to um, produce a plot of this for example, for a talk, a workshop, a seminar, or even for a paper. So let's see how this is possible to create high quality plots starting from this um, visualizer. Well, lastly, I haven't really mentioned that this visualizer by default does not show all data, um, but starts with a lower threshold, and then this can be increased or decreased. The reason is that, like, if you're um, plotting many several hundred thousands data, this can be time consuming. So we want to keep performance quite fast, we want to have quite good performance while visualizing data, and we avoid overloading of data. But still, you can also select your fraction of the compounds from here. So now we want to define our plot, so we can change some of the parameters. We can change the colors. So for example, here we have different pastel colors. Okay, so now we have pastel. But with pastel, we see, for example, that the background color is not that great. So we might want to change the background color. Again, this is not ideal for visualization, so we might completely remove this background color, and that's it. Then we have a number of different features. So we might wanna enlarge the cross size, so to make it more visible, the position of some specific compounds that we are interested in. Or we might want to decrease the marker size because we want to make the plot a bit more dense. So in this case, we see, let's change the color then. In this case, we we may want to, on the other hand, increase the fraction of the compound, so to have a well-defined quality plot. Then well, we might want to reset the symbols. And that's how we can generate a plot. Then we simply click on this print button, and then we are going to create a plot that is called Windows from our browser will appear, and then you can download this plot with this format here. And scale represents the resolution of the plot. So increasing this value will increase the resolution of the plot. So this was all. I really hope you enjoyed this short video, and that you learn how to use the visualizer, and that you will be able to deploy it on the AI Toolkit. Thank you for your attention.